What's up, my chemistry students? Mrs. Thompson here, and this is our last unit in chemistry. It's redox. I'll teach you about what redox is and how do you find oxidation numbers. Alright, so first, what is redox? Well, redox is actually short for oxidation and reduction. So these are certain types of reactions that occur where electrons are moving. And so it says here, reactions where electrons move between atoms and change in oxidation number. Okay, so we need to know what oxidation and reduction is. First, let's just talk about oxidation. Now, you may have heard that term before, that things oxidize, like iron oxidizes and forms rust. And what happens there is the iron attaches to the oxygen, and the iron itself loses electrons. And so oxygen is good at making things lose electrons. And so since it's not only at the addition of oxygen that causes other atoms to lose electrons, we have a broader definition for what oxidation is. It's the loss of electrons. When this happens, the oxidation number will increase, and we'll get into that more later. For reduction, there is a gain of electrons, and the oxidation number decreases. The oxidation number gets reduced. To memorize this, there's a couple of mnemonics. Here's my favorite one. Leo says GR. And so why Leo says GR? That's just because loss electrons, so lose electrons, oxidation. Gain electrons, reduction. So just remember, Leo says GR. Lose electrons, oxidation. Gain electrons, reduction. So what about oxidation numbers? An oxidation number is the number assigned to an element that gives its apparent charge. So it's a little different here. We've talked about their charges. This is its apparent charge. Okay. When we were talking about charges, we were talking about ionic compounds. And so if we're talking about ionic compounds, the oxidation number is its charge. So sodium and chlorine get together, form an ionic compound. Whatever their charges are, that's their oxidation number. For molecular compounds, and that does include polyatomic ions within an ionic compound, those are based on how the electrons are distributed around the molecular atom within the molecule. The way we write oxidation numbers is we write the charge first, the plus or minus sign first, and then we write the number. So there are certain rules for assigning oxidation numbers. You have them, so we need to fill those in. 1, any element all by itself is just 0, and that includes diatomic elements. 2, group 1A metals will always have a +1 charge. Now notice that says metals. 1A means we're looking at the periodic table. Okay. 2A, so these are our alkaline earth metals, those are always a 2+ or +2. Halogens in group 7A are usually a -1. So it's not an always rule, it's a usually rule. But they tend to be positive when they're with an oxygen. Monatomic ions are what their charge is. So if we have Na+, then the charge on that would tell me the oxidation number. If we have a hydrogen, it's usually a +1 when it's with a nonmetal. However, when it's with a metal, it tends to be -1. Oxygen is usually a -2, except when it's in a peroxide. So a peroxide would look like this, H2O2 or Na2O2. And then fluorine is always a -1. This one is an always rule. Even though it's a halogen and it says usually -1, fluorine is the exception. It's always a -1. All right, next what we need to do with our problems when we're finding oxidation numbers is we'll notice that the sum of the oxidation numbers for any neutral compound is 0, just like the sum of the charges is 0 for an ionic compound. For a polyatomic ion, it's equal to the charge on that ion. Now, if those rules are just not enough, we need one more rule, and that is, and this is very rare, that the oxidation number of the more electronegative atom in the molecule or a complex ion is the same as the charge it would have if it were an ion. So you would go back to the periodic table and figure out what charge should it be if it were just an ion in an ionic compound. All right, so let's do some examples. Okay, so we have Br2. This is an element all by itself, so therefore it has an oxidation number of 0. Okay. What about copper? All by itself, 0. Potassium, all by itself, 0. Sulfur, all by itself, even though there are 8 of them, 0. Okay. Next row, sodium with a plus charge. Now, because it's all by itself, it would normally be 0, but it has a charge, which means it's an ion and not just an atom. So we just look at the charge that it has. It's plus. So this is a +1. You do have to, for oxidation numbers, write the charge, positive or negative, and the number always. Okay. Sulfur is a 2- charge in number 6, and so that means its oxidation number would be -2. Okay, notice its charge is written with the number first. Oxidation number is written with the negative first. All right, so here we have some compounds, and let's see if we have rules for each thing. Well, sodium is a group 1A metal. I know that by looking at the periodic table, so it's a +1. Bromine is a halogen. It's in group 7A, and those are usually -1. So we'll go ahead and put -1. Now, if we added these two together, the +1 and the -1, well, that would give me 0. Another thing about this one, it's a metal plus a nonmetal, and so it's an ionic compound. It should be what its ionic charges are. Okay. Next one, magnesium oxide. We have another ionic compound. Let's see what rules we have. Magnesium is in group 2A, so it's a +2. Oxygen is in group 6A. Because it's ionic, I can say it's -2. Or I could say, well, oxygen is usually -2, so there. It's -2. And then when we add these two together, the sum of the oxidation numbers should add up to 0 for a neutral compound, and it does. +2 and -2 add up to 0. All right, so let's try the next one. CO2. Here we have a molecule, so it's not about its actual charges, but its apparent charges based on how the electrons are distributed around the atom. Okay. So, carbon. I do not have a rule for carbon, but I do have a rule for oxygen. It's usually -2. So I'm going to put -2 above the oxygen. Now, this isn't the overall charge of the number of oxygens and its charge. It's just the charge on each oxygen, the oxidation number for each oxygen in this compound. All right, so what we have to do is figure out what carbon is. We'll just write it as X for now. We'll do some algebra. So hopefully you remember your algebra. It's just basic algebra, not hard stuff. Okay. So I have 1 times X. 1 times X because I have only 1 carbon. Okay. And then we're going to add 2 because of this 2 times -2. So the number of oxygens times its oxidation number is equal to, well, the sum of the oxidation numbers has to add up to 0 because I do not see a charge on this compound. All right, so then I just have to do some rearranging. This is going to equal -4, okay, and then I want to move it to the other side. So 1 times X is X. This becomes -4, and then I move it over to this side by doing the opposite of what's going on. So I'd add, so that's +4, which means that carbon is a +4. And notice I'm not just writing 4, I'm writing +4. All right, let's do the next one, NH3. I do not have a rule for nitrogen, but I do have one for hydrogen. And that rule is that hydrogen is usually a +1 when it's with a nonmetal. So we're going to put +1. Okay, because nitrogen is a nonmetal. All right, so then we don't know what nitrogen is. I'm just going to put X for now. You can put X or you can leave it blank. All right, so we have 1 nitrogen, so 1 times X, plus 3 hydrogens. There's 3 hydrogens in the formula. subscript of 3 times the oxidation number for each hydrogen, which is a +1, and that has to add up to 0 because it does not have a charge. All right, so I do my math. That's x plus 4 is equal to 0. Move over the 4. Excuse me, x plus 3 is equal to 0. Move over the 3 by subtracting from both sides, and x is -3, which makes nitrogen a -3. Okay, this next one's slightly different because it's a charged one. It's a polyatomic ion. It has a -1 at the end. So we're just going to treat it like we did earlier. Oxygen is still a -2 because it's usually -2. And then nitrogen is our x. So we have 1 times x plus 2 times -2 because I have 2 oxygens and each one's -2. Instead of saying it's equal to 0 this time, because it has a charge, it's equal to -1. It's equal to that charge. Had this been like a +3 up here, I would have written +3 here. Okay. All right, so then some rearranging. 1x minus 4 is equal to -1. Move over the -4, and we get that x is equal to +3. So that's just +3 for nitrogen. Okay. And so our goal in all of these is to figure out the oxidation number for each atom in the molecule. Sometimes your problems will just say figure out the oxidation number for one of them. It's usually the one that you have to do the calculation for. All right, next one, HNO3. So we know hydrogen is usually a +1 when it's with nonmetals. So we'll put +1 there. Oxygen, usually -2. Nitrogen is something we don't know. We don't have a rule for it, so it's X. So make sure you keep referring to those rules. All right, so 1 times +1 plus 1 times X, because I only have 1 nitrogen, plus 3 times -2 because I have 3 oxygens, each one's a -2. And that's going to equal to 0 because this doesn't have a charge. Okay, so then I combine everything. 1x minus 5 is equal to 0. X is equal to +5. And so therefore, in this case, x is a +5. So notice this oxidation number is different for nitrogen in number 11 than it is for number 12. Okay, calcium carbide. Let's see. For calcium, we have that group 2A metals are +2. And what about for carbon? We don't have a rule for carbon, so we have to figure it out. Now, we can start doing this without doing all the algebra, because you can do these in your head. So let's think about it. If calcium's a +2, and I have 2 carbons, all this has to add up to 0. So what does each carbon have to be? Well, each carbon has to be a -1. So there's my oxidation number for carbon. Okay, now we have zinc and hydrogen. This one's different because with nonmetals, hydrogen is +1. But with metals, hydrogen is a -1. So this is zinc, and zinc is a metal. Well, if I have 2 hydrogens and each one is a -1, that would be a -2 altogether. So zinc must be a +2. Okay, so these just keep getting a little bit tougher. Next rule we haven't covered is with halogens behaving positively when they're with oxygens. So bromine is normally -1, but because it's with oxygen, we're going to figure out what positive charge it has. All right, so oxygen would be a -2. We're going to do this in our head. So 3 times -2 gives me -6 on this side. Now, if this were neutral, didn't have a charge, this would be a +6. But it does have a -1, so we need 1 less, so that's going to be +5. All right, next rule. Here we have 2 halogens together, chlorine and fluorine. So chlorine and fluorine normally have a -1, but we're not going to put 2 negatives together. We need something that's positive. Well, we have a rule that says fluorine is always -1. So that means chlorine has to be the positive one. So if we have 3 of those, 3 times -1 is -3 altogether, so chlorine must be a +3. All right, last one. All right, this one's a little different because let's check out our rules. We have one for calcium, that's a +2. We do not have a rule for carbon, and we do not have a rule for nitrogen. So we have 2 things without a rule. So we're going to have to do some math here. Okay, so the rule that we have is when all other rules fail, what you do is you look at electronegativity, and the one with the highest electronegativity gets its normal charge. And so if we look up in this chart, periodic table, electronegativity increases from left to right and from bottom to top. So here's our highest in electronegativity. So between carbon and nitrogen, nitrogen should have a higher electronegativity. So we're going to give nitrogen its normal charge. Well, it's in 5A, and that's 3 away from the halogens, so that would be -3. So it'd be -3, -2, -1, and then 0. So nitrogen would be the -3. And then we just have to figure out what carbon is. So I'm just going to go ahead and do the math part for this one. It's a little more complicated. All right, so we have 1 calcium, it's just a +2. We have not one carbon, we have 2 carbons. So that would be 2, because that gets distributed in 2 times x plus 2 times -3 gives me 0. Combine some terms, 2x equals +4. So each x is a +2, so that carbon is a +2. All right, ask some questions in class.